So if we have a position function that's given as a vector valued function, for instance, so r of t is equal to x component x of t, y of t, z of t, then if we want to know the velocity, right, so the velocity vector, that is just the derivative of the position vector, right, rate of change of position with respect to time. Exactly like it was, right, without vector valued functions. So we just do component by component. So x prime of t, y prime of t, and z prime of t. So notice that velocity is a vector. And if we want to talk about speed, then we would write, right, the v without the, right, vector notation above it. But I'm still going to use the v for velocity, right, speed. So this is going to be speed, no vector. It's just the magnitude, right? So that's the magnitude of the vector of the velocity, right? And so if we had to do that, right, we x prime squared plus y prime squared plus z prime squared, right? Square matum rutum. Oops, sorry. There we go. Okay. So, and then same with, right, acceleration. So acceleration is the first derivative of velocity. Looks like my pen just decided to die. Velocity. And so then that would be the second derivative of the position function. Vector, vector, right? So it would be x double prime, y double prime, and z double prime. Okay, so that's kind of it. It's the same, right, as you knew from before. So if you differentiate the position vector, you get velocity. Differentiate velocity, you get acceleration, right? Acceleration is the rate of change of velocity. Velocity is the rate of change of position. So differentiating, going down the list. Okay, so here's an example. Let r of t be given by the formulas t cubed for the I hat direction, e to the 2t for the j hat direction, e to the t for the k. Let's just find the velocity and the acceleration vectors. Right, so the velocity vector, yeah, no big surprise, right? 3t squared, 2e to the 2t, remember your chain rule, e to the t. Okay. And acceleration vector, just do it again, right? So 6t, 4e to the 2t, chain rule again, e to the t. Okay. Could we find an expression for the speed of that particular one? What would the speed of, right, that particle be if it's following this path right here? Right? It'd just be a big old square root, and then we'd square everybody and add them up. It doesn't look like it's going to be anything super nice for us. All right, 4e to the 4t plus e to the 2t. Right? So that expression there, right, at any given time t, you could plug it in and come up with a velocity then. Okay, now we can go the other way. So if we know the acceleration vector, if we're given the acceleration vector, we can, right, integrate, we can go backwards to find the velocity vector and the position vector. So here's our example. So a of t, e to the t, comma 2t, comma t plus 1. And then usually you're going to be given these initial conditions. So when we integrate our acceleration, right, when we find the antiderivative, there's always that plus c part, right? Well, this time there's going to be that plus c vector, right? So that constant is actually a constant vector. So there'll be an I hat, j hat, and a k hat component. Now, you can do these a couple of different ways. I like to just go term by term and look at my, my constants. So I'm going to do a c sub x, a c sub y, and a c sub z, right? And then we'll find those values to make our initial conditions true. So to find our velocity vector, we're just going to integrate our r vector with respect to t. I'm sorry, our a vector. Sorry, caught that. So what we'll get then is e to the t, right, plus c sub x, comma, so I'm going to integrate the next part, put some vector brackets around it. So integrating 2t with respect to t, so that'll be t squared plus the y component of your constant vector. And then for my z, I'm going to get t squared over 2 plus t plus c sub z. Good? Okay, well now we're going to look at our initial condition here, right? We know that v of 0, sorry, that should have a vector on it over here too. So v of 0 is 1, 0, 1. So we're going to find what those c sub x, c sub y, and c sub z are. Okay, so at 0, just looking at your x component, right? So for the x's, 1 equals e to the 0 plus c sub x. Okay? So e to the 0 is 1, so I've got 1 equals 1 plus c to the x. It looks like c to the x, or c sub x is 0. Okay? Now we'll do the y's here. So for the y's, right, I've got 0 equals 0 squared plus c sub y. Well, it looks like c sub y is 0 as well. Okay, well, that's not very interesting. And how about c sub z? So for my z's, am I still on here? Looks like we're shooting for 1. So 1 equals, plugging a 0 in for our t's, right? So we'll get 0 plus c sub z. So it looks like c sub z is actually 1. So this means that our velocity vector is going to be e to the t, right, plus 0, t squared plus 0, and t squared over 2 plus t plus 1. Okay. So there is our velocity vector. Now to get the position vector, we are going to, again, right, integrate our velocity vector. Oh, v of t with respect to t. There we go. Okay, a little sloppy, but that's okay. So we're going to integrate, right, e to the t squared over 2 plus t plus 1 with respect to t. And our initial condition, I'll copy it over onto this page so we can see it. We've got 2, 1, 1. Okay, so here we go. Term by term. So r of t. So we'll get, oh, that's a t, not a 0. We'll get e to the t plus c sub x, t cubed over 3 plus c sub y. And the next one there is going to be t sub 3 over 6 plus t squared over 2 plus t plus, right, your constant, c sub z. Now we're going to grab that initial condition. So we know if t is 0, x is 2, right? So we're just going to go piece by piece. So for my x's, I know 2 is equal to e to the 0 plus c sub x. So 2 equals 1 plus c sub x. So it looks like c sub x is 1. And do the y's. So the y value is 1, right, when t is 0. Here's my y component. So 1 equals 0 cubed over 3 plus c sub y. So it looks like c sub y, also 1. And finally, for my z's, right at 1, my position is 1 when t is 0. So I get 0 cubed over 6 plus 0 squared over 2 plus 0 plus c sub z. So it looks like c sub z also 1. So just to make it look nice, we can write our position vector then. So the x part is going to be e to the t plus 1, y component t cubed over 3 plus 1, and our z component t cubed over 6 plus t squared over 2 plus t plus 1. Okay, so that's how you can use initial conditions and integrating to work your way back from an acceleration vector to a position vector.